Good afternoon to everybody. The time to start our second last session of our conference. Please invite you.
So welcome everybody. It is a pleasure to be here. My name is Emilio Pisanty. I will be chairing the session, and it is an absolute pleasure to introduce Tim Lee from Canada, who will be talking about advancing polarization, speckle-based attention of melanoma in vivo with deep learning. So, Tim, please go ahead.
Okay, thank you, Chair. Let me just share my screen. Nothing sharing. Stop sharing.
So we can see your screen, but it was in edit mode.
Somehow couldn't. Okay, here. That's one moment. Okay, here. Let's try this one. Okay, share. What happened? Oh, okay.
That's working.
Okay, that's better.
No, previous one was better.
Yeah, okay. Do you see my screen? Is that okay?
We see your screen, but it's in presenter mode.
It's in presenter mode. Okay,
yeah.
Let's see. Okay. Okay. How about that?
Yeah.
Okay, great. Okay, thank you very much. Okay, yes. So I will talk about the using deep learning to analyze the polarization speckle-based detection of melanoma in vivo. So let me get my pointer. Okay, yeah. Okay. Okay, yeah. Okay, good. So here is the outline of my talk. First, I will go over some background information of polarization speckle, and we'll touch on the skin cancer, and then a little bit about deep learning. How does it work? And also then I will go into the analysis method using deep learning to analyze the speckle images. Oops. And then first I will talk about the some older methods called moment analysis. Actually, this one is not a deep learning approach. This one is what we call the machine learning approach. And then I will go over the convolution neural network and the convolution neural network with attention block. And finally, I will give a short conclusion. So first about polarization speckle. Okay, so well, the whole thing will start with the laser speckle. And I'm pretty sure this audience knows when we shine a coherent light into a media, especially rough media, and then it would generate a speckle pattern. And if we use a CCD camera to capture the 2D speckle pattern, we will see something like this. And for our application, we would like to use a skin structure. So we will actually measuring skin. So skin is really complex as an organ. It has a multiple layers. Well, you have 2 to 3 layers, depends how you call it. Actually, the first 2 layers really skin. This one, the subcutaneous is the fat underneath the skin. So the 2 layer of the skin is the first layer is called epidermis. That is the layer. Actually, inside it have multiple layers of different cells. The very top layer is the dead skin, or we call the corneum. And then follow that, it is the squamous shell. It is the flattened cells. And then when you move down, then you will see the squamous shells, and toward the bottom, there is something more round-shaped cells called the basal cell. And also there's the keratinocyte and the melanoma site of the cells, and they are right above the what we call the epidermis and dermis junction, and this the skin upper here will grow upward, and when we pass the junction, we go to dermis, and dermis have a very rich set of the collagens, and also have a rich set of the vessels. So as you see, there's a very complex organs with the structures. So when we shine some coherent light into the skin surface, what happened? And we will immediately get the surface refractions. Uh, and that is a small percentage of refraction. A majority of light will penetrate through the skin, through the cells, and do further scattering, and eventually we emit out of the skin. So what happened with those light? So the light we shine is a coherent light, and it will have coherent length, and the surface refraction will have a similar coherent length as the incoming light. But the light, when we go through uh, the uh, the inside the skin will penetrate through the inside the skin, the coherency will reduce sharply, and the remittent light will have a very low contrast speckle pattern compared to the speckle pattern generated by the surface refraction. And when we look at the polarization aspect of the laser light, and if we assume that we have a linear polarized laser, and it is polarized along the y direction, and then when we look at the surface refraction and the polarization, it is similar to the incoming light. So the polarization is maintaining. But the light that penetrate through the skin and get lots of scattering, the polarization is scrambled. So when we put things together, then we will have what we see is a speckle field if we capture it using a CCD camera. And this speckle field of course, is an interference pattern field. It will have a random phase and random intensity, and also more importantly, it have a spatial random polarization. So this is really is a polarization speckle field. And over the years, we have worked on a number of prototypes to analyze the speckle pattern. This is one of the earliest prototype, and it used two lasers, a red and a blue lasers. And when they shine through the skin, we use a diaphragm to do the spatial filtering. And when the light, returning light coming back, it will direct it to the two cameras, and each one will have a polarizer in front of it. And one of the polarizers have the co-polarizing filter, and the other one have the cross-polarized filter. So one of the camera will capture a co-polarized channel, the other one have a cross-polarizing channel. And the typical demo will see the speckle image just like this. We have a high contrast co-polarized channel and very low contrast very low signals over the cross-polarized signal. The integration time is about 5 milliseconds, so it's relatively fast. Oh, it's very fast. And okay, so that is the device whether we talk about today. And even though do have other devices, but okay, now let me move on. Give a quick summary of the skin cancer. Okay, WHO point out that skin cancer is the most common cancer worldwide, and it have 1.5 million new cases in 2022. Actually, that is, I would say that's a lower bound number. I think the number is higher. Usually, the WHO is more conservative and only report a more conservative number. And the incidence rate increases steadily over the past decades, even though there are numerous campaigns all around the world. So there are three types of skin cancer that we're particularly concerned of. One is called basal cell carcinoma, as shown at the top here, and followed by the squamous cell carcinoma and melanoma. And it is the bottom one, the melanoma, that we have more concern. The reason it is this type of the skin cancer, it could be fatal. Fortunately, there is much smaller number of people who have melanoma, uh, and only about 300,000 new cases worldwide. But it causes about 60,000 deaths a year. And let's look at the tables on your right-hand side. Then this one is show the age standardized incidence rate per 100,000. And then we will see that, of course, Australia's, but particularly Queensland, it is the melanoma capital. It has the highest number of cases, and followed by New Zealand. And in Canada, Prince Edward Island, that is the eastern provinces in Canada, it has the highest rate. And Minnesota of the USA has the highest rate. In Europe, Norway has the highest rate. And all those three areas has a rate about, well, a little bit about 22 or 20, well, in the 20 range. And for Ukraine, well, the number is very low. They enjoy very low melanoma rates, only about five per 100,000 people. That is a very low rate. But when I would look back at the rate at the 10 years ago, is only in the three per 100,000 range. So it seems like melanoma have been increased quite rapidly in Ukraine, and increased definitely more than half. So, and the melanoma rate, the 5-year survival rate is high if it is detected and treated early. And so what it means, if people with who has the disease can survive more than 5 years. It's over 90% people can survive more than 5 years. But if you happen to have a late stage of melanoma, then the survival rate would drop to 15%, as very low. So that's why early detection is the key. So the key thing is to detect the disease as early as possible and start the treatment. And so what I show you is melanoma is very common, or skin cancer very common, but dermatologists are not. There are very few dermatologists worldwide. In Canada, there's only, I think, 600 people, 600 dermatologists. So, or should I say practicing dermatologists. And also melanoma looks easy to detect, but they are not. And in one of the study, it showed the physician assistant would need to biopsy almost 40 lesions before able to identify a melanoma case. Dermatologists, they do better, but still over 25 biopsies to identify one melanoma. And then some of the people will have many those lesions, or what we call moles. What we're going to do with it? Are we going to cut out every single one and do biopsy? So this is a challenge. So that's why we want to develop a non-invasive technique. Actually, there have been many people have developed different non-invasive technique, but I'm particularly interested in using the polarization speckle technique. And so here it shows some polarization speckle image of various different skin lesions. A is show melanoma, and then B and C are the squamous cell and basal cell carcinoma. All these three are the most common skin cancer. And then D is the nevus. This is the benign lesion. It looked like melanoma, and also the doctor or people could confuse between the two, and especially at the earlier the stage of melanoma. And E shows separate keratosis, and again is another benign lesion, but again is often confused with melanoma. And also that is we later on we also interested in the looking for another lesion called actinic keratosis. That it is a people think that it is the actinic keratosis. Many of them could develop into squamous cell carcinoma. So we consider that is also malignant. Okay, so what the doctor need? Doctor need something very simple, easy to use device. And the dermatology, because there are so few of them, there are so many patients, they want to make the diagnosis fast. And then what they want to do is to want to differentiate melanoma from the most common benign look-alike, like particularly the nevus and separate keratosis. And also they want to identify whether a lesion they see is whether malignant or not, or cancer or not. So for cancer, a lesion is cancer, they have to treat immediately. For the non-cancer lesion, they do not have to need to treat it. So that is what the doctor always want to ask, whether they when they see a lesion is whether they should treat the lesion or not treating lesion. So that's all the background. So now I'm going to talk about the deep learning. Deep learning is a now is computation technique that model with the human neuron, and he is to depict a human neurons in the left side of the screen, and the neuron will have a many input, and when this neuron receive the input, it would do some kind of thresholding and determine whether it will fire, this neuron will be fired or not. And then if it's fired, and then we send it to the downstream neurons. And the neuron will form a network, many of neurons working together to make a decision for our body. So, but of course, we work on, it's not the real neuron, we work on the artificial neuron. Typically, this is a simple diagram to depict that. And so here we assume that we have a neuron, it will have all kind of input, m of them, from x1 to xm, and each input will have a weight, and the weights could be different. And when the neuron receive all those signals, it will do the summation. It will do a weighted sum, and then it will use a bias that it is the level to control whether this neuron will fire or not. And the firing of the neuron is based on the activation function. And there are numbers of activation function, and I list only this few common one. One is the simple threshold one, or sigmoid, or Roulet, or 10H. And then when we put all those neurons together, and so a circle is representing neurons, so we will put all the neurons together and form a network. Then typically we will have an input layer, a layer that will allow the input, receiving input, and the output layer is the output of the neuron signal. But in between, there could be many different layers. Those are the hidden layers. And typically, a deep learning network will combine many neurons. And the output of the network, we will call it is a function of f it depends on the input, of course, but also it depends on the free parameters of each neuron. Remember, each neuron have a parameter of the weight of all the input from all the input, and also a bias. So we will. So this is a rather very complex function with many parameters, and the network is trained by a set of the training data that also come with the corresponding labels. What we call the label is the ground truth. So it's trained with a set of data that we know the input and we know the output. And the training basically will find a set of W's and B's that minimize the average difference between the output function and the corresponding label for all the training data. So in other words, the deep learning method will always find it's actually the minimization problem. It will try to minimize the difference between the network output and the labels. And by doing so, it will try to find the best configuration and the set of the W's and B's. And so many people think traditional want to compare the traditional machine learning and the deep learning. And traditional machine learning is come before the deep learning, of course, and it is a model-driven method, and that require domain knowledge. I think that is the one we know for a long time, that we try to do the modeling, and then we need the domain knowledge to do the modeling. So typically, the designer will design a set of features for each situation. And those features could be specially designed for the situation, so they are called the handcrafted feature. And the designer will have a full control of the feature selection and the feature extraction, because those are hand-picked features. So typically, the modeler or the designer will only model a smaller set of the features, and the training data set and the time was moderate. But on the other hand, the deep learning, it is the data-driven method. It will try to learn the knowledge from the data. So remember what what the deep learning is? It tried to minimize. If you have a data set with known input and output, you try to find a network that minimize the network output and the ground truth. So also the deep learning allow us to learn the features. Those called the deep features. Those are usually those features can be obtained in the hidden layers. And this is an optimization problem. It guarantees it will find the minimum between the deep model and the learning data. So that's why in some sense, this methods always produce the optimal result. Compared to the traditional machine learning, it won't able to guarantee that. But on the other hand, the deep more in the traditional machine learning, because you handcraft those features, you know what each feature is. But in the deep learning model, the deep features sometimes shouldn't say sometimes, often are difficult to interpret. There could be a large number of the free parameter, the W's and B's, and it could be in a range of millions. And so the training data set and time and the requirement is more stringent. We require large training set and using a long time. But both methods sometimes could overfit the problem. So there's the concern of overfitting. It is same for both. So what we try to do is we use our prototype that I shown earlier. It has two lasers, but actually I forgot to mention these two lasers. It actually operated sequentially. So you can think of this prototypes actually being two two separate devices. And then we want to measure the skin, and that will produce a speckle image like this. And we want to find a method to analyze those speckle image. Particularly, we want to measure the skin lesions, and we want to see whether able to detect a melanoma lesions versus whether it's a separate keratosis or device, or whether the lesion is cancer or non-cancer. So first, I want to go into some more traditional method called moment analysis, just for the contrast. We have done that in the quite early work in the 2013. So remember that that the prototypes able to produce two speckle image, or their intensity speckle image. One is co-polarized, one is cross-polarized. And actually, for these two channel, we carefully align them so that we can combine them and form and compute the degree of linear polarization. Or actually, also paper we call it depolarization. We actually look at the depolarization. And the equation is very simple, and I'm sure all of you are familiar with it. Basically, it's the difference between the co-polarized and the cross-polarized, and then normalized by the sum. And each operation is operated on pixel level. So at the end, we will have a degree linear polarization image. And once we have this image, we can compute the moments of it, and we can compute all four moments, and that is should be quite straightforward. And then when we have those moment value, we use them to differentiate between benign and malignant lesions. So this one, it is a traditional machine learning technique. Basically, we will use the feature we identify is the moments of the degree of the linear polarization image. So we conducted a clinical study, and we recruit 214 patients from the skincare center, which is a part of the Vancouver General Hospital that in Vancouver, Canada, where I live and work. Among them, there are 25 melanoma patients, and 11 squamous cell carcinoma patients, 31 basal cells, and 76 neoids, and 71 separate keratosis. In total, 214. So the steps are quite straightforward. We measure the skin lesion and the adjacent normal skin lesion using the blue and red laser sequentially, separately. And then we will we will generate the polarization speckle image, create a degree of linear polarization image, and then compute the moments. And then we're analyzing using what we call the receiver operation characteristic analysis, the ROC analysis. And here then we find out that actually all four moments can be used to separate out melanoma from separate keratosis, BCC, and SCC. And particularly the fourth moment, it is particularly good to separate out melanoma and the separate keratosis SK. And using the red laser, it have the accuracy of 87%. And using the blue laser, the accuracy is about 84%. It works very well. It actually performed quite well. Maybe it outperformed many methods, and particularly with the dermatologists. The expert dermatology will basically, well, we have a similar performance, but it will outperform the GP and the general dermatologist. Yeah, okay. And so let's just do a summary. So moment analysis, we are very excited with the result because this experiment showed that we can actually extract the diagnosis information from the polarization speckle image. And the technique can differentiate between melanoma and SK. But unfortunately, it won't separate out cancers and non-cancer and melanoma and Levi's. So we need to find a better method to do the other two jobs. So here we come into the deep learning approach. And so that's several years later, we applied deep learning, most into a similar data set. Actually, because there is several years later, and then we managed to collect more data. So we have 37 melanoma, 30 of SCC, 44 BCC, and we included actinic keratosis I also mentioned earlier. And so in total, those we consider those are the malignant case, 122. And then we have 91 device and 105 SK. And the benign lesion is 196. And so what we apply well, nowadays probably is people consider this is traditional, really a straightforward deep learning method. But this study was done a number of years ago. So we use a ResNet 101. And then it is 101 layers deep learning network. And then also we want to compare this method with the traditional machine learning, the SVM, random forest, and KNN method. And the goal is to classify the degree of linear polarization image into cancers and non-cancer classes. So, those are the layers, and then the final output layer will be only two, will be cancer or non-cancer. And so this is the implementation details. So we have 318 skin lesions. And actually, some of the lesion, we take the more than one speckle image. So total, we have over 1,000 speckle image. And among them, there are 448 malignant and 339 benign. Speckle image, the size are about 1024 by 768. It's quite a large image. And then we want the input size to only do 224 by 224. So we managed to able to crop a speckle image into 9 patches. And then we will follow the convolution, the conventional data augmentation method. We do the left-right flipping, the top and bottom flipping, and then random rotation. And then we have a 100,000 patches. Here I want to point out the deep learning require large number of data, but our data set is way too small. So, but we make use of the speckle image, then they are sort of a stationary of an entire image. Then we can and we can able to crop it, and it still represent the speckle image. And even with the 100,000 patches, they're still quite small for deep learning. So we did a 5-fold cross-validation. And we split out those data sets into something called the lesion-based splitting. So what does it mean? It is if a patch belongs to a lesion, or if the patches all the patch belong lesion, we will always put it into either training or validation or testing. No patches from a lesion will be in a training, and some will be in validation or testing. that would cause a problem, a data leakage problem. So we ensure there's no data leakage. And then here's the result. We show that we found that the ResNet have very good accuracy, over 80% accuracy for the ResNet. And sensitivity, well, it's slightly below 80, but 79. And then, but the specificity is a little bit higher. And so the results are very encouraging. So it seems like the deep learning, the ResNet, able to analyze cancers versus non-cancer using the using the polarization speckle image. Unfortunately, the same thing cannot be said to the other traditional machine learning method, the SVM, KNN, and random forest. The results are much lower. So here, let me quickly summarize this one. So we found that deep learning can extract more information from the polarization speckle image, and it can differentiate between cancers and non-cancer. But how about melanoma and nevi? The previous one, it works somewhere, somehow, but it's not ideal. So lately, we work on something called the attention-based deep learning method. This is more advanced deep learning method. We have just got the results, and we have not published them yet. So please keep all the data confidential. Okay, here, remember in the previous method, when we work on the deep learning or the movement method, we first have to compute the degree of linear polarizations. And we actually, the cos and cross polarization channel, they are carefully aligned. And then, but there is extremely hard to align in the wavelength level. So there is error, and for sure. So, but in this method, we instead compute, we do not explicitly compute the degree of linear polarization method. We use a cos polarizer and cross polarization separately and input them separately into the network and using something called the attention. And the attention method basically will try to find out the best alignment as possible and then pass the features and we extract those deep features and do the diagnosis. And the results is quite interesting and surprising too as well. And so here we call our models SA square, and it have accuracy of 95%. And also we test out three others deep learning methods, and then they result in the accuracy in the 80% range. But the traditional machine learning, the result is much lower, only from the 60 to 70% range. So, okay, so I come to the conclusion. So it seems like deep learning can potentially extract the hidden diagnostic information from polarization speckle image and could be a effective tool for skin cancer detection. This is a very long project, expand many years, so I have a long list of acknowledgement and also acknowledge many of the sponsors. And here is my research team. Particularly, I want to acknowledge the Luda, and she and I to work on we start up the project. Here is my PhD student, Daniel. He built many of those prototypes. And Yuhan Wang is the postdoc fellow who applied deep learning to the techniques. So thank you for your attention. And I think that is all I prepared.
Thank you, Tim, for a very interesting talk. We have time for one or two quick questions. We have a hand up from Aristide Dogariou.
Yes, very interesting results, Tim. I have a couple of quick questions about the physical setting, please.
Okay.
Is this measurement done in the specular direction of your reflected light, and how far is the camera from the surface of the skin? Is it in an imaging geometry, or is free space propagation? And so from
It is a free
I
space.
kind of missed it.
It's a free space. We're based on the free space theory.
And is it
So,
on the specular direction?
sorry,
Is
from
it
the
in the
specular direction. That's right.
specular
Yes.
direction or not? Yeah.
Yeah, from the specular direction. That's right. Yes, it is.
And also, if I may, I kind of missed the purpose of using a red and the blue laser. How
Okay.
far
Yeah.
apart are these wavelengths? You know, red and blue
Yeah, that's
kind
right.
of big.
Okay. Yeah, because everything is wavelength dependence. Like, so at the beginning, that is one of the earliest. Yeah. So we want to test out the two wavelength, the common wavelength. So one is red and the blue. So we just happen to, especially in the well, when we first started the project, we do not have large experience. So basically, yeah, we just pick up these two. And actually, matter of fact, we will later on we want to test out other wavelength, but we don't have the chance to work on that yet.
So the algorithm does not combine the information acquired with the two colors, right?
No, those are the decided so that they are take this separately. But actually, it is we can combine them in sense. Yes, we can, but we haven't done that because they are even though they're taken sequentially, but they take it immediately without leaving the device. The device is right on the lesion.
Okay.
So each one is only take about 5 milliseconds. So 5 milliseconds for the red, and then the next one 5 milliseconds for the blue. So there's very little movement between the two.
Interesting.
Mhm.
All right.
Okay, thank you.
Thank you.
Maybe time for one more quick question.
Yes, I have to Professor Lee. Professor
Yes.
Lee, hello.
Please.
Yes, and I'm curious about that you said in your presentation that even first statistical moment, like a variance,
Yes.
is able to communicate with some lesions and so, because this is a little bit not understanding for me, because speckle field is something like a statistical structure, and the first moment it's even it's only the difference between of some intensities, and what is the diagnostic efficiency of using this in your presentation of only the first moment?
Could you repeat your question? Not quite follow it. Yeah. So your question about the use of the second and the third moment?
The first moment. You said
The
that
first moment.
all the fourth moment are efficient to communicate with some changes in the
Yes.
in the speckle field. But the first moment, it's only the difference between some.
Oh, the first moment. Yes. Yes. The first moment. But somehow in our data, seems like we managed to find the difference between the using the first moment. That could be it is well, we don't have the good explanation for that, but that is how the data find. It could be some due to the lesion color. Melanoma typically they tend to be black, and then it's separate characterosis and tend to not so black. It could be like that.
But you deals with the speckle field, so it's only, for example, from your experiments,
Yeah,
it's
true.
only
Yeah, it is
black
circle field.
and white, yeah, and so
Yeah,
on.
that's right. Yes. Yeah, I
So
would.
we should I think that's a good point to stop and move on to the next talk. I'm sure there's more to discuss. It's a really interesting topic, but in the interest of time, we should move to the talk by Razvigor Ossikovski. So I see he is present. So Tim, could we ask you to unshare and then Professor
have I not
Ossikovski?
unshare? Okay, sorry.
No, it's good. Yeah.
Hello, do you hear me?
Hello. Yes,
Hello? Let
we
me
can hear
share.
you. And we can see your screen.
Perfect. Okay. Full size. Is it okay like that?
Yep, that works. Yeah. So Professor Ossikovski is going to talk to us about phenomenological interpretations of Mueller matrices in polarimetry from both theory and experiment. So please, floor is yours.
Let me first thank the organizers for giving me the opportunity at this nice conference. And to apologize, I couldn't attend in person. So the talk is about the phenomenological interpretation of Mueller matrices. And it is a strongly reduced version of a tutorial I've been regularly giving on this topic. And while I'm partially the author of some of the theories, I can say that all experiments come from collaborators and which are my colleagues essentially or students. So it's a very, very long list. You can see here. So all these people have contributed with their measurements to establishing the theories or to checking them. So what we are talking about, first of all, we talk about polarimetry. So what is the experiment here? We necessarily have a light source. We shine light on the sample, and this light must have a definite polarization state. So we use a polarization state generator to produce the definite polarization state. Then the light is either transmitted or reflected through the sample, and the polarization state is analyzed by a similar device as the generator, but which we call polarization state analyzer, which projects the reflected or transmitted polarization state, and it creates an intensity, which is detected by the detector. So this is the measurement equation of this generic setup. So if we shine 4 Stokes vectors, which, as you know, describe polarization on the sample, and if we describe a sample by a 4x4 Mueller matrix, and we project the resulting states on the Stokes vector, we get 16 intensities. And from these intensities, we can derive this Mueller matrix, which describes our sample. So if we use 4x4 states or more than that, we'll get the full matrix. If we use less states, as people know, most of you know, most likely we'll be doing ellipsometry. So for instance, instead of measuring all 16 elements, we'll be measuring only 3 of them. And from them, we can deduce the ellipsometric angles. So now we'll be talking not about ellipsometry, but about full polarimetry. So on one hand, we have polarimeters, which are readily available. We can buy them from several companies. They are fast, they're reliable, they're easy to use, they have nice softwares. And on the other hand, we have complex structures which we measure, such as anisotropic materials, crystals, gratings, biological and organic samples. So we had a very nice example in the previous talk on biological samples. And also turbid media, complex solutions like phantoms, etc. So these media are getting more and more complex. And the classic physical approach has been, we measure the experimental Mueller matrix, we build an electromagnetic model which relates the physical properties of the structure we've been measuring to the Mueller matrix, and we invert to get the physical properties. However, the model complexity is proportional to that of the structure. So sometimes the electromagnetic model is simply impossible to build, or is too complicated. And the question is, what can we do with the Mueller matrix if we don't have a model? How can we retrieve an information from the polarimetric measurements without any preliminary knowledge? So the answer is, we have a 4x4 real Mueller matrix. We can apply simple linear algebra. We have all studied in university, second year usually, to decompose this Mueller matrix into simpler matrices, which are more meaningful to us. So what are these simpler matrices? One of them is called the blue one, you can see here, MD, which is di-attenuation. So what is di-attenuation? This is the change in the amplitude of the electric field along two perpendicular directions, x and y, say, or horizontal and vertical. And so what is the example, classical example of di-attenuator? You all know it. This is the polarizer, partial polarizer, or full polarizer. Another simple Mueller matrix we all know is the retardant Mueller matrix. So it doesn't change the amplitudes, it changes the phases between the two electric fields along two orthogonal directions. And we need also a third matrix, which is the so-called depolarizer, which introduces decoherence between the two components of the electric field. So it reduces the degree of coherence and it depolarizes the light. So if we shine fully polarized light on a depolarizer, we will necessarily get partially polarized light. So these three building blocks, we can multiply them and we can get the measured Mueller matrix, or conversely, we can take the measured Mueller matrix and we can decompose in these three building blocks. However, as you know, in linear algebra, A times B is not equal to B times A, so there can be constructed three products out of these blocks. And these three products lead to different decompositions. So let's see how they work on a quite academic example due to my colleague Antonello Di Martino. So consider a cuvette or recipient filled with milk. So milk acts as a depolarizer essentially because it scatters light. And to reinforce the signal, we have put a metal plate at the bottom of the cuvette, so to have more reflected signal. So this is a reflection measurement configuration. So this metal plate at the bottom acts as a depolarizer, acts as a reflector, increasing the depolarization due to the milk. We have also put a mica plate, which acts as a retarder, which is nothing but a retardation plate. And we have put a tilted coated glass, which acts as a di-attenuator. So why does it act as a di-attenuator? You remember that the Fresnel reflection and transmission coefficient depend on the incidence angle. So when we tilt the plate in transmission or reflection, we will get P polarization different from S polarization. So if we measure the Mueller matrix of this composite sample, this is how it looks like in reflection configuration. And we can see that all three basic elements, retarder, depolarizer, and di-attenuator, appear in most of the elements of the Mueller matrix. So these building blocks are shuffled between all 16 elements. So how can we separate them? We apply one of these product decompositions. We get three more matrices, di-attenuator, retarder, and depolarizer. We calculate, the di-attenuation, the retardance, and the depolarization, which are scalar properties. Actually, these are vectors, but we calculate their length, so we get scalars. And if we image the di-attenuation, the retardance, and the depolarization, we discover straight away the elements we have put in the cuvette. So the di-attenuation shows clearly the tilted plate. The retardance images clearly the microwave plate, which was drowned in the milk. And the depolarization shows the metal plate, which reflects the signal and which increases the depolarization coming from the milk. So this is an example on how you can separate a very complex response into 3 elementary responses, just by simple linear algebra. So this was the academic example. So let us move now to a more realistic one, which is a biological sample, in this case, a meat slice, and again, image it and apply product decomposition. So we use 2 of them, one with the attenuator coming last, and the other one with the attenuator coming first, because they don't commute. And let's look at the results. So in BND, we have the depolarization, which is the same for both decomposition. However, in the attenuation, in A and C, we have clearly different responses. And the response in A has much more contrast, has better imaging properties than the response in C. So how can we understand this? The mu slice behaves roughly as the product of depolarizer multiplied by a attenuator. Why so? Because when we send light to the mu slice, there is volume response and surface response, essentially, as we have seen very well in the previous talk, by the way. So the volume response generates the depolarization, and this is the same for both decomposition, while the surface response generates the attenuation. And since the surface response is preserved only when it is at the end, not when it is in the beginning, because in the beginning it is shuffled by the volume response, we have a better imaging processes for the attenuation when it comes at the end, not when it is put in the beginning. So this is an example of how we can use these product decompositions to increase the contrast, the contrast of the surface response, to enhance it from your overall measured response. So what else can we do with matrices besides multiplying them? We can, of course, sum them. So there are several sum decompositions which decompose a generally depolarizing mirror matrix as a sum of non-depolarizing mirror matrices. So these non-depolarizing mirror matrices are either retarders or the attenuators or a combination of both. But what is common to all of them is that they are non-depolarizing. So they transform totally polarized light into totally polarized light. Here, we don't need any depolarizers, simply because if we add Mueller matrices, we get automatically depolarizations, because addition of Mueller matrices is equivalent to loss of coherence. So it is equivalent to introducing incoherence. That is depolarization. How can we put to profit this decomposition? A classic example is when we measure a sample which is smaller than the spot size. In this case, we have a grating and a substrate, 700 nanometer period grating on crystalline silicon substrate. And if the spot of our system is smaller than the grating, we can measure the grating alone, which is on the right, or we can measure the substrate, which is next to the grating, which is on the left, and which turns out to be log diagonal. So everything works fine. However, if the grating is too small, the spot size will be larger than it. So it will fall same time in the substrate and the grating, and we will measure a mixture of substrate and grating, which is shown here. And we can apply the sum decomposition to decompose this mixture into a linear combination of a grating and a substrate. And these are the results. So we can see the mixture in black. So this is a spectroscopic measurement, not an image like before. We can see the grating, which has been measured separately. And you can see also in blue the decomposed grating, which closely matches the grating which has been measured separately. So we can, having a mixture, we can retrieve the two components just by linear algebra without knowing the individual responses. So the individual responses I have shown have been measured with a very small spot size. Another example, again taken from biological systems, the cuticle area of Cetonia or rata beetle. So this is a classic example of a circular polarizer. So if you have a look at the Mueller matrix of this cuticle area, you see many, many dots, and these dots correspond to circular polarizers. So +1 is blue and red is -1. So we can see red here and blue here. So indeed, this beetle behaves like a circular polarizer, which has been known for at least 100 years. And it's still an active area today, studied by my colleague Hans Sarin. So, however, if we have a look at the areas in between these dots, you will see that the response is more complex. And if you want to model this response electromagnetically, which is partially possible, you can model this by a multi-layer structure, and you can obtain a response more or less close to what you measure. However, if you model this response phenomenologically, it turns out to be very simple. It is just the linear superposition of a circular polarizer and a plane mirror. So when we're on the dots, we have only circular polarizer, so alpha is equal to 1. And when we are in between the dots, we have a linear combination with about 50% each, plane mirror and circular polarizer. So we see that such a complex multi-layer structure is very simple from a phenomenological point of view. It is just a superposition of a polarizer and a mirror. So what else can we do with matrices besides summing them and multiplying them? We can take the medium and we can slice it into very small infinitesimal slices, and we can multiply the responses of these slices to get a kind of continuous product decomposition, unlike the discrete product decomposition we've seen before. So this has been done by the fathers of modern polarimetry like Jones and Garasym. So if you do this, you get this differential equation. So we switch from this capital M mirror matrix we measure to this small m differential mirror matrix. And if we assume that the medium is uniform, if you assume that this small m matrix does not depend on z, so z is the propagation direction, then the solution to this equation, as every student knows, is exponential. So if you take the matrix logarithm of this mirror matrix, you will get L, the logarithm, proportional to this differential mirror matrix by the thickness. So why is it interesting to do this? This is so because this differential mirror matrix, the small m, contains the same building blocks we have seen before. It contains diattenuation and retardants, so in red and green here. However, we don't call them here diattenuation and retardants, we call them dichroism and birefringence. So it is all the same, so dichroism is the difference in the real parts of the refractive index, in the imaginary parts of the refractive index, and retardants or birefringence is the difference in the real parts of the refractive index. So what happens if we have depolarization? Then this matrix logarithm contains two parts, M, Lm and Lu, non-depolarizing and depolarizing part. This M part contains the mean values of these properties, which we call elementary polarization properties, which are dichroism and birefringence. And this Lu part contains the depolarizations due to the fluctuations of the properties. So if you assume that the properties are fluctuating, so instead of having well-defined values, they have some means and some differences from the mean, we can construct the second-order moments, like to form variances and covariances for every property. And we can construct the covariance matrix, which looks like this for all these properties. And then it turns out that this covariance matrix is proportional to this Lu part, to this depolarizing part. So when there are no fluctuations, when all the deltas are equal to 0, then this covariance matrix will be simply 0, and then the whole Lu matrix will be 0. And instead of having mean values, we'll have just the properties themselves. There will be no fluctuations. And also, according to this theory, the mean values should vary linearly with the thickness. So the Lm part should vary linearly with d, while the Lu part, U like uncertainty, should vary parabolically with G. So it should vary like D square. So this was easy to check on a biological sample. So the student performed histological cuts of human skin models at different thicknesses, 3 microns, 6 microns, 7 and 10, and measured the Mueller matrices and plotted the mean values and the depolarizing part and the non-depolarizing part for this sample as a function of the thickness. And we see that the non-depolarizing part, which is actually essentially only the birefringence property, because the histological cut of human skin contains collagen. So essentially we have only retardants or birefringence, varies linearly with the thickness according to the theory. And the depolarization varies parabolically, again, according to the theory. So we can assume that this theory describes correctly the experiment. So now I have no more time to tell more stories. So I just want to summarize. The phenomenological modeling approach appears as a powerful tool for the analysis of Mueller matrices. If you don't have any model, or if the model is too complex, or if you don't have any preliminary information. And secondly, this phenomenological modeling is not just playing with linear algebra, but it helps you to get a deeper physical interpretation, a better physical understanding of your sample, because it decomposes your system, your response, into simpler responses, which are more familiar to us. And people often ask me which decomposition should I use. So it all depends on what you're measuring and how you measure it. So even if you think that you don't know anything about your sample or your system, you still know. You know that you measure in transmission or in reflection. You know that your system contains a discrete or continuous medium. You also know if your system is depolarizing or not. So you should use this knowledge to choose the right decomposition. So there's a book on all this. But instead of reading the book, the best is to send me an email and we can discuss on your data. So you can join the team of all experimentalists who contribute to the developing of these theories. Thank you very much for your attention.
Thank you so much, Razvigor. That was an extremely interesting talk. I think we can take time for one quick question. I think Professor Mohun is potentially interested. Yes, go ahead.
Thank you very much. Very interesting report. And maybe my question is not principal, but when you test your approach, we used only 3 test objects. What are the reasons of his choice? Because it seems me that process of reflection is very complex. We have interaction between polarization and coherence and so on and so on. Can you say something about this?
Sorry, I'm not sure I got the question. So what is the reason for measuring in reflection instead of transmission?
Of choice of such test objects. Only 3 types. Depolarization object.
Oh, yes. Why there are only 3 types? It is just because we can perform only 3 operations on the electric field. We can either change the amplitude, change the phase, or randomize amplitude and phase. That is why we get 3 types of responses.
I see. Thank you.
Okay, thank you very much. I think we can move on to the final talk of the conference. It's by Yuri Ushenko, who I think is in the call. There you are. So Professor Ossikovski, could we ask you to unshare your screen? There we go. And then Yuri will be discussing phase scanning Jones matrix thesiography of dehydrated blood films. So whenever you're ready to share your screen,
yes, dear colleagues, one moment. I try to try to oh, sorry. Oh, excuse me, one moment.
So we can see your screen.
Yeah, colleagues, do you see my screen?
Yes, we can see your screen
Yeah.
in edit mode.
Yes, one moment. Yeah. This one?
Perfect. Ready to
Yeah,
go? The floor is
exactly.
yours.
Yeah. Sorry for 1 minute of waiting. Yeah, dear colleagues, my next presentation is strongly connected with the previous presentation of distinguished professors. So it connected with phase scanning of Jones matrix thesiography, or so-called mapping of dehydrated blood films. So my name is Professor Yuri Ushenko. I'm from Chernivtsi National University, and I'm also partly depend from Department of Physics, Shaoxing University from China. So let's start with my presentation, because my presentation is the final presentation, and we have only, I think, 15 minutes, yes, for me. Yeah. So before final closing ceremony, so the outline will be the following. So we will start with introduction, with basic equations and theoretical remarks. Next, we start with experimental setup and measurement technology, and with the objects, so-called biological fluids, phase object, and consider the 3D Jones matrix scanning method. After that, we will start with statistical analysis of such Jones matrix maps, and something talk about the objects of investigations, experimental results, and discussion in order to fundamental aspect and applied aspect, and to make some conclusions. So in this report, I would like to talk about the one of the most important system for ensuring the vital activity of human body, so-called is a set of biological fluids that involved in all our metabolic processes. In biological fluids, there are high-speed changes in the molecular composition and the nature of interaction of various components in physiological, extreme, and pathological conditions. Any both physiological and pathological processes in our living organisms basically represents specific changes in the structure of a protein and other organic molecules. Such changes are the most informative in the study of homeostasis at the molecular level, and can serve as a basis for the diagnosis of various diseases at the earliest stages, because it is very important. Any morphological research in biology and medicines focuses mainly on cellular elements, while the morphological analysis of biological fluids, the basic systems of life support, has remained inaccessible for clinical practice until recently. The existing microscopic methods for processing the geometric structure of biological fluid images or maps contain only general algorithms, the results of which does not depend on the specifics of the processed images. At the same time, no less important information about the architectonics of supramolecular self-organized networks of biological fluid molecular crystals, their optical anisotropic properties, which can be extracted by polarization introscopy, turns out to be absolutely unknown, inaccessible. Overcoming of this problem can be provided by new laser methods of three-dimensional interference polarization mapping, so-called 3D digital holography methods, using, in this case, by Jones matrix formalisms and digital layer-by-layer holographic reconstruction of optical anisotropy maps of biological products. This investigation is aimed at developing a new method of three-dimensional matrix mapping of blood facets in order to search for algorithms for layer-by-layer reconstruction of optical anisotropy maps using the Jones matrix, and to determine on this basis the statistical parameters, so-called markers, that are most sensitive to pathological changes, for example, in this research to papillary thyroid carcinoma in supramolecular networks of biological crystals. So let's start with some basic equations and theoretical remarks. So according to in our case, according to traditional concepts, in a single scattering approximation by a polycrystalline film of a biological fluid, this can be represented by a sequence of partial lever with 6 types of optical anisotropy in all cases. So-called linear and circular birefringence, LB and CB, and linear and circular dichroisms, LD and CD. This LD and CD and also LB and CB are consisted in biological layer in all times, and it cannot be separated at once. So, and the common Jones matrix of such a biological layer, it's a also polycrystalline film of biological fluid. In our case, it's a blood drop, can be represented by a Jones matrix 1. You can see it here, where the Q is a generalized anisotropy vector here, and where the elements B0, 90, B45, 135, and A clockwise and counterclockwise circulation could be connected with the parameters of linear birefringence and linear dichroisms, also as a circular birefringence and circular dichroisms by equation 3. So the algorithms for calculating the elements of generalized Jones matrix W, as you can see in equation 1, includes the irradiation of a polycrystalline film sample by linearly polarized beams with azimuth 0 degree. For this state, the Jones vector is the following 1, 0, and 90 degree, the Jones vector is the following. So these two orthogonal components of electric field is presented by equations 4 and 5. You can see it here. The physical algorithms of transforming the polarization state within the Jones matrix approach are the following. It's birefringence, which is connected with linear birefringence and circular birefringence. It's depicted here in the equation 6. And dichroism, this one is connected with linear dichroism and circular dichroisms, which are, these mechanisms are presented in the equation 7. In what follows that the equations 6 and 7 will be called Jones matrix maps in our research, and it depicted by T, A, and B, and it connected with already with linear birefringence, circular birefringence, linear dichroisms, and circular dichroism. The experimental setup for doing such a interference inspection using the Jones matrix formalism are presented here. It's the specialized imaging Mach-Zander interferometer for polarization interference mapping of Jones matrix elements. So the issue of this interferometer, there is that we have used, we need to use the strain-free objective that not disturb the polarization state, and two branches with some polarization state generators in reference beam and in the sample beam here, and now and here before the CMOS camera we have a polarizer which can measure, which will be able to measure the two orthogonal components of electric field vector. Okay, so after that, the two states of linear polarization are sequentially formed in the irradiating and reference laser beams here. And for each of the polarization states of P and R, so orthogonal, yes, two partial interference patterns are recorded through the polarizer analyzer P, yeah, here before the CMOS camera, with the transmission plane orientation at angles of 0 and 90 degree. So for each this partial interference distribution, we perform a two-dimensional discrete Fourier transform on the image, and here we have calculated elements of Jones matrix. W11, sub 11, sub 21, sub 12, oh, sorry, and sub 22. Also, after that, we are able to do the statistical analysis of these elements through the calculating the statistical moments from the first to the fourth orders, from the mean value, dispersion, the coefficient of skewness, and the coefficient of kurtosis. And concerning our objects, so we will consider whole dehydrated blood polycrystalline films, so-called blood fascie, which consist of two main parts, blood plasma and shape elements. The choice of such object is connected with both fundamental and applied aspects, because from the point of fundamental approach, so in the process of dehydration and molecular cell assembly, various architectonics of optical anisotropy of polycrystalline networks of various constituent blood fascies are formed. The obtained data on the polarization manifestation of such an optical properties of such networks can be used to determine the totality or the set of physical and quantitative relationship between the topology of optical anisotropy maps and the specifics of the biological crystals ensembles of special single angular structure. From the point of applied approach, the quantitative parameters in our works, we used a set of statistical moments from the first to the fourth orders, which characterize the Jones matrix thesiograms or maps for various conditions of light scattering in the volume of samples, and this can be used as a markers of different diagnoses of various pathological condition of the human body. This you can see the parameters of this dehydrated blood films. So it's an attenuation or extinction coefficient here, and the depolarization degree here in the percent. So here you can see the first results of fundamental approach. So we can measure due to the decode the Jones matrix to linear birefringence and circular birefringence of different samples. So, and to analyze the statistical structure and of linear and circular birefringence, also linear and circular dichroism. Figure 2 and figure 3. These results are presented for decoding the information in the phase layer of our sample in the phase plane pi divided by 8, for example. So we can do the phase scanning in not only integral image, but inside the something like a set of images with the phase shift pi divided by 8. Due to the applied approach, we can form two sample groups of healthy donors. Control group 1, 17 samples, and patient with papillary thyroid carcinoma experimental group. Second one is also 17 samples. So we have such an experimental results. So from obtaining the parameters of linear and circular birefringence and circular and linear and singular dichroism. So here we have a statistical analysis due to the previous slides of analyzing such a group of parameters. And you can see that, for example, for linear birefringence between of these two groups of samples, we are able to achieve 88% of accuracy. And concerning the circular birefringence, also circular, yeah, we are able to achieve the 90% of accuracy. So, the main results and the main conclusions of this report are the following: that the Jones matrix mapping algorithms for such types of optically thin biological samples, like polycrystalline blood facies, are developed and experimentally tested. And so mentioned types of blood facies were examined and achieved some results. So, and the most sensitive markers to changes in layer-by-layer topographic structure of such a blood facies, phase, and amplitude anisotropy are established. There are a third and the fourth statistical moments of linear birefringence and dichroisms within the statistical moment. So, and this one also, these results can be used in clinical practice and in a physical understanding of the physical structure of biological fluids and also biological tissues also. Thank you very much for your attention.
Thank you so much, Yuri. We have immediate question from Mikhail Ugorsky. Please go ahead.
Thank you, Mikhail Ugorsky, Trinity National University. First of all, thank you for a nice presentation. And I have general question. Why do you use Jones matrix instead of the Mueller matrix, which are more common applied in polarimetric studies?
Yeah. Thanks for a nice question, because this one is the choice of using the Jones matrix formalisms. Now, in our case, because we are studying the optically thin biological objects, so the depolarization is not very high, and the coherence properties remains almost the same. And in this case, we are able to, and also we are decoding this information about the amplitude and phase information. So we are able to use not Mueller matrix, for example, for a high depolarizing, for example, objects, but we are able to use the Jones matrix formalism in this case. Thanks.
Understood. Thank you.
Thanks. And we can move to one final question from Aristide Dugariu.
Yes, a very quick one. Very nice statistical analysis. Thank you for the presentation. Do I understand correctly that it is relying on a delta correlation spatially assumption? Did you, because that histogram from everything starts, each element is treated independently, right? Have you observed in the experiments any kind of special correlation between all of those polarimetric properties that you are recovering? Which relates to the practical aspect. Is that objective imaging the surface or not?
Professor Degario, thank you. This question is in progress in our
It's
group.
complicated, I know.
Yeah, not complicated because this question is in progress in our group because now we have first results, but not in this conference. I think that we will see in other conferences. Really, because the information decoded. For example, we are talking about the structure of some sample we need to investigate. But really, in simple objects, it could be talking some simple approaches. But for such a complex object like a biological tissue on fluids, the main information consisted in some intercorrelation between some parameters. And now, for example, I think that in the future conferences we are talking about correlation between some matrix elements and, for example, Stokes correlations and so on will give more information. And even for now, I can talk that we have some results that intercorrelation between some, for example, Stokes elements and mutual matrix elements will give more sensitive results, but we need to explain this from the physical point of view from the object. Yeah, thanks.
Thank you. Thank you. I'm very interested in this high order
because
I agree. That's extremely interesting. Okay, folks, I think we need to wrap up the session. Professor Singola is probably has some words first.
Thank you very much. Thank you very much. We finish our last talk, and then we move on to the closing ceremony. It will be with another link. Please switch on another link, and then we start in a few minutes the closing ceremony. Thank you.
Thank you very much. See you there.
See you later.